Here we go. Okay, am I set? Do you see the slide?
Yes.
Good.
Okay.
So, so today we'll be finishing up treating scattering processes. More than scattering, today we're going to do radiative transitions, so optical processes. I don't know if you want to call it scattering, interaction of light with matters. And then we'll move on finally to transport. So let me get my pointer here. So finally we're going to get to transport. It's a subject that it's extremely subtle. The idea would be ideally to derive a semi-classical transport equations that has been used in various forms and shapes to simulate electronic transport in semiconductor devices. I will mention it quite in detail. You cannot derive it, but at least I would like to show how one can go from quantum statistical mechanics, so a quantum description of our crystal and electrons in our crystal, to this semi-classical transport equation. But today we're going to talk about radiative processes. Why did I move so far? Okay. Having, not today, but probably in the next few lectures, we'll be talking about how to solve the transport equation. So today we'll derive it, so to speak, in quote unquote, because as I said, it cannot be strictly derived, but I'll show you the path that one can follow, and then we'll see how to solve it. And there are very many ways, so we'll go, some methods will be described in detail, some will just give a rough overview. For the last part of the class, I still have to decide a little bit what I want to stress. There are two subjects that I would like to discuss. One is electronic transport in a low-dimensional system, starting from silicon inversion layers to keep it in a more usual situation. But nowadays, well, historically, quantum wells have been a subject of great interest, mainly because they're used in high electromobility transistors and, of course, optical devices, especially lasers. So that's an interesting thing to do. And this is a situation in which the confinement into small region, whether it be the quantum well or the field that confines electrons in an inversion layer, the silicon dioxide interface, these quantum effects, so to speak, they're not effects that affect transport extremely strongly, directly. You can still treat the problem in the transport problem in a semi-classical picture, just in lower dimensions and with a few corrections that, of course, you have to make in order to account for the confinement of the carriers. So this is not really quantum transport, although in the literature sometimes you will find people talking about quantum transport, meaning instead semi-classical transport, but in a quantum confined situation. This is a subject which is quite interesting. The other one is to deal instead with quantum transport, genuine quantum transport, which is when quantum effects are important, roughly speaking, along the transport direction. That is a subject which is the subject of a lot of interest, a lot of work. One has to ask whether we will really need it eventually, at what the channel length scales, in which devices. There are some devices in which this is extremely important, of course. A few examples of quantum devices, such as resonant tunneling diodes. This is the prototype. In conventional devices, I don't think that we yet have any experimental evidence that we need quantum transport. Yet, ultimately, one thing that we may need it in molecular devices, very small devices, definitely you need it. So I have to decide a little bit to what to do, and please feel free to let me know if you have a particular interest, what subject you would like me to discuss. The idea is that this class that I'm teaching usually, I taught it here in the States, and the length of a semester is a little bit shorter We have 14 weeks, two 1 hour and a quarter lectures per week. So it comes out a little less. And I have more time here to discuss some subjects that usually I don't get to discuss, which are extremely interesting. Notice that I fixed the numbering. I realized that I had this outline with the wrong numbering for quite some time. Okay, so first let's talk about radiative transitions. I will not go into too much detail, but I would like to discuss and spend more time instead on transport issues finally. The interaction of light with matters is a subject that you can discuss for many lectures. Here we will focus on a specific case, which is considering electromagnetic radiation of energy which is just around the visible spectrum. So from infrared to ultraviolet, not too far in infrared, not too far in ultraviolet. So we're talking about photon energies which are on the order of 0.1 eV or so, up to maybe a little bit less if you want to talk about long wavelength radiation, which sometimes is used for telecommunication, to a few eV, which is the case that you may consider, for example, looking at optical absorption in photovoltaics, in solar cells, where you have to deal with the solar spectrum, and there is, of course, some a mild UV component, definitely violet and blue components, so of the order of a few eV. And we'll consider the interaction of electromagnetic radiation of these wavelengths only with electrons. So we're not going to deal with anything that, for example, you deal with in nuclear physics and you want to see what a gamma ray may do to a nucleus in your system. So we're not going to go there. So a very, very narrow scopus that we have here, narrow aim. We have not dealt with any of this type of interaction so far. We've dealt with electron-phonon interaction, electron impurity, electron-electron. So either elastic or inelastic processes in which the energy, so to speak, remains in the lattice. You either distribute it among gathered electrons or the energy that the electrons acquire, say, in being accelerated by an electric field goes into the lattice. Here we're dealing with an excitation which is external to the system. Light which is impinging on the lattice, or a lattice which is in which electrons are driven strongly off equilibrium, and you might have light emission via recombination, electron-hole recombination processes, and so energy leaves the lattice and goes into empty space via the electromagnetic radiation. So to treat the problem, we will have to write the Hamiltonian that describes the motion of the electron in the presence of an electromagnetic wave. So we'll consider simply an electromagnetic wave, so we can ignore the electrostatic potential, consider only the vector potential. And if you remember, that's something that we discussed some time ago, there is a way which we call the minimal coupling to couple electrons with electromagnetic radiation described by the vector potential A, and that is replace the momentum operator that you have in the Schrödinger equation, if you wish, with this expression. So you add the electromagnetic potential. This should be divided by c, the speed of light, depending on the units that you're using. Again, we'll ignore the electrostatic potential because we'll be dealing purely with electromagnetic waves. So we take the minimal coupling and we consider the electromagnetic field weak enough, which is the case for single photon processes in this range of wavelengths that we're considering. We consider only the first order or the leading order coupling between these two. So we expand the square, the term proportional to a square, we leave it out, and we're left with a term which is the dot product of P dot A, which I describe in this way. P, of course, is the momentum, so will be minus h bar times the gradient, and that's what I've used here. So this is our equation of motion, Schrödinger equation, if you wish. If we want to go to second quantization, we'll consider, as usual, the fields psi, which is the Schrödinger field, and the field A, which is the field associated with the quantized electromagnetic field that we saw a few lectures ago. This is the field equation, again, looking at taking a second quantized perspective. Now our Schrödinger equation represents instead a classical equation for classical fields, psi and A, and now we quantize the fields by finding a Hamiltonian density. Before that, we need a Lagrangian density, and then we proceed through the usual second quantization, canonical quantization process. I think we saw already what is the Lagrangian density associated with a Schrödinger field. Here we simply have to add the term which represents the interaction of the electrons with the electromagnetic field. We do the usual transformation, Legendre transformation, to go from the Lagrangian to the Hamiltonian. In this case, we have densities, Lagrangian density, Hamiltonian densities. So our Hamiltonian density, just the perturbation part, is just this term. It's essentially the dot product of the vector potential with the gradient of the field, the divergence of the field, so the gradient of the field multiplied by the field square. So essentially there is a density, but there is a momentum operator in between. And that's what we will explicitly find in the following. So the total Hamiltonian that in this picture describes the interaction of electrons with the electromagnetic field is given by the integral of the Hamiltonian density, which is the integral over space of this quantity. Now, remember, these are second quantized object. So what we have to do is to go back to your notes and look at what was the expression for the Schrödinger field and the vector potential A that we found having second quantized these two fields. The vector potential A was essentially given by the sum of an annihilation or recreation operator of a photon. Sorry, I will probably make the mistakes of saying phonon instead of photons. So photons here, a photon of momentum q and of wave vector q and polarization lambda, times a prefactor. I remind you that this prefactor essentially comes from the canonical commutation rules. I told you many times that they set the scale of the problem. This looks very much like what we saw for phonons, except that we had a deformation potential there, but in interaction. But this is essentially the prefactor that describes essentially the magnitude of the electric field or the vector potential associated to a single photon. And then we have the Schrödinger field, which is this portion here gives you an annihilation operator. This is a creation operator. So notice that we have some coupling constant, which is this term, which is essentially an overlap factor that we'll discuss in a minute. The coupling of the interaction, it gives us the strength of the field that the electrons feel. And then we have this term here, which is, if you remember, very similar to what we saw for the electron-phonon interaction. So the process is take an electron with wave vector k, destroy it, annihilate it, creating a new electron with wave vector k prime, and the difference in the momentum k minus k prime comes out from the momentum h by q that we give to the photon. So it's a photon emission process in which we create a new photon that didn't exist before, or a photon absorption process in which we destroy a photon that already existed. And of course, we have to do this sum over all the possible bands that we're considering in our crystal, all the polarization of the photon, all the position of wave vector of the photons, and all the electrons that we have in the system. And this is an overlap integral. It's a little bit different from what we had before because there is a gradient over here, which is the momentum essentially that is coming, momentum of the electron, which is coming from the gradient that we have in the Hamiltonian density. Okay, so of course the only non-vanishing, non-zero matrix element that we have to consider when we want to consider these sort of radiated transitions are those in which we already have an electron with wave vector k. I'm ignoring spin here. If you have spin, you have to add an index that describes spin. We have already we don't have an electron in the final state k prime by Paul's principle. And then, of course, we have to take the matrix element of the photons that exist. And this will be giving us the usual thing, exactly the same that we saw for the electron-phonon interaction, will give us the Einstein coefficients. So the absorption the matrix element associated to absorption would be proportional to the square root of the number of photons that we have around. For emission, we're going to have the square root of the number of photons that we have around, stimulated emission, and there is the extra one, which I remind you comes from the normalization of the Fock states in the boson Fock space associated with the photons, which gives us spontaneous emission. So this actually is where the Einstein's coefficient came from. We saw them for phonons before. They are the same because it's the same for all bosons, but historically, of course, it was the work that Einstein did in order to find how you should get equilibrium in dealing with the black body spectrum between matter and radiation. I forgot to mention that this little e here is also what comes out from the second quantized form of the vector potential. This is the polarization of photons. Photons have spin 1, so they can have polarization up or down, or if you want, circular polarization clockwise or anti-clockwise by forming a linear superposition of the up and down. But this is the polarization vector, which is dotted with the gradient that we see here of the field. Okay, so this is our final expression for the non-zero matrix elements, but not final. That's what we have to start dealing with. And we have this rather messy integral, which is the integral over the entire volume of the lattice of the gradient of the block function, the initial one, the final block function, and then there is this the oscillatory component of the photon. So this describes the spatial variation of the electromagnetic wave. Now, as I said, here we're focusing on near optical photons. If we go and look at what is the wave vector associated with the photon, is roughly of the order of, it's inversely proportional to the wavelength. On the contrary, the k vectors that we're dealing with for the electrons are inversely proportional to the lattice constant. In the range of wavelength that we're interested in here, so excluding X-rays and gamma rays, in near visible range, the wavelength of the photons, it will be much larger. We're talking about microns compared to tens of nanometers, which is the lattice constant. So the wave vector, the magnitude of the photon wave vector is much smaller than the length scale, the momentum length scale that we have. So the good approximation is to assume that actually this Q is 0. The wavelength is much bigger than the size of a cell. Everything that happens in this integral is on the scale of the size of the block function, and these are the orbitals. You remember that these are essentially the remnants of the atomic orbitals that constitute the crystal. So these vary on a length scale which is of the order of angstroms. This instead, this term varies on a length scale which is of the order of micron or just below a micron, whatever it is. So essentially we can take this as a constant over the cell, over this length scale. And this means that we're going to consider vertical transitions. So here I show the band diagrams for a direct gap material, gallium arsenide, an indirect gap material, silicon. So let's look at this first. If we assume that Q equals to 0 here, we will see that momentum conservation, crystal momentum conservation, will require the K and K prime are essentially the same. So we can have transitions which are only vertical. These lines, strictly speaking, should be slightly tilted, but the amount by which we have to tilt it is proportional to the ratio between the lattice constant and the wavelength of the lattice that we are considering. So the tilting will be smaller than the width of the line that I drew here. And we can have transitions, which of course can also be intraband, interconduction band transition, and so on. Typically, we will consider a situation in which the valence band is full, the conduction band is empty for absorption, or if you want to consider emissions, just we have a few carriers which are excited somehow, for example, in a laser by being injected in a p-n junction and being accelerated by the field, and they will populate the conduction band and they can emit photons by decaying into the empty states in the valence band. So we'll be mainly considering transition between the valence band and the conduction band. But again, you can have interband transitions. Actually, there are situations in which you can have light emission near the drain end of a field effect transistor driven at a large drain bias, in which electrons can be accelerated to sufficiently high energies in a conduction band, and they can emit photons by actually intra-conduction band or interband, but between conduction bands. But the transitions are always vertical. In a direct gap material, so we want to talk about the absorption spectrum, for example, which we'll deal with in a moment. The threshold in which light begins to be absorbed happens for wavelengths which are shorter than a critical wavelength, such as the energy corresponding to that photon is the band gap. And maybe a little bit less that we'll talk about. I'll mention briefly excitons at the end. In an indirect material, things are very different, and that's why, for example, silicon is not used much in optoelectronics. You need something else. Usually the transition, the threshold of your absorption spectrum will be given by whatever is the gap. For silicon, you see that the gap doesn't change much. It can be much larger here, but in this region is about a little bit more than 3 electron volts, and that's where you have your threshold for the direct transitions. But you can have a softer threshold, which involves higher order processes in which you need some momentum to go from the gamma point to the minimum of the conduction band. This wave vector here, this change of momentum, has to be supplied by some other process. That's why typically phonons. And this is why it's a higher order process, because you need a two-step process. Okay, so this is our approximation here, replacing this e to the minus IQR with 1, with unity, assuming that q equals 0. And this is what we call the dipole approximation. So this is the same expression, but now I've gotten rid of my exponential, just setting it to 1. This is the term that now we have to work a little bit about. So we can expand it. The gradient acts here on the block function, wave function of the electron in band N and wave vector k. Of course, we have a term which takes the derivative of the exponential and another term that takes the derivative of the periodic component. This term is usually very small. It's usually neglected. It depends a little bit on the k vector we're dealing with and so on, but typically this is something that also varies with an exponential. These are functions. Since this term here, e to the minus I k minus k prime dot r, oscillates fast when k and k prime are very different, the major contribution to this integral comes from the region in which k and k prime are very close. In this case, the block functions here, if the band indices are different, so we're dealing with a different band, and typically that's what we deal, then this will be essentially an integral or a dot product between two eigenstates of our Hamiltonian, which is a Hermitian operator corresponding to different eigenvalues because we have different bands. So this term becomes very small. Again, its main contribution comes when k is similar to k prime, and when n prime and n, the bands are different, this becomes 0. In the limit in which k and k prime are identical, this is exactly 0. So we're left only with the first term. And you realize that the first term is what we may call a momentum matrix element. It's essentially the matrix element of the gradient. Okay, the momentum we have to multiply by minus IH bar, but it's a momentum operator, and it's a sandwich between the two block functions. So it's a momentum matrix element. So we can plug it back here. Again, we're replacing the gradient of the entire block function with the gradient only of the periodic component. The advantage is that now we can restrict the integration only over a single cell, doing the usual trick that we saw many times before. We replace the variable r that we're left over here with the translation vectors of the lattice. L denotes cells, plus whatever remains, which spans only a unit cell. So we do the integration only over the unit cell. This term, as usual, gives us the number of cells. So here we have the number of cells divided by the volume of the crystal, which becomes 1 over the volume of a single cell. And this is the momentum matrix element in a single cell. And again, we get a momentum conservation having done this integration over here, because we have assumed vertical transitions. So the integral over R of the two exponentials gives us a delta function. This is equivalent to saying that the transitions are vertical. Then we dot the momentum matrix element with the polarization of the photon, and here is the usual prefactor, which is coming from the amplitude of the electromagnetic field associated to a photon, which is given by these factors times the square root of this coefficient, and then we have the usual Einstein's coefficients. That, of course, the matrix element will enter squared in our expression for the transition rates, and so we recover just the Einstein's coefficients. Good. So as I already pre-announced, this is actually a momentum matrix element, except for a few constants that I put in place here. So just the normalization volume, the volume of the integration over the volume of the unit cell of the momentum matrix element over the block functions. And this is how we can simplify the expression. Notice here that this momentum matrix element is quite important. I mentioned before several times that usually, and that's what we did in calculating electron phonon matrix elements, electron impurity matrix elements, we ignore these terms. We said, well, it's an overlap integral. If the initial and final wave vectors of the electrons are not too different, it's roughly 1, so we'll ignore it. I only gave you some warning that in intervalley processes, or when you go to high energy and you have strong and non-parabolic corrections, this may become, so when K and K prime are very different, will be quite different from 1. So it reduces the magnitude of the scattering process. But usually it's not a huge effect. Here it's a huge effect. For example, you remember the selection rules that you might have seen in the past in some other class, where and that comes from momentum conservation, the absorption or emission of a photon requires a change of the momentum of the electronic states by plus or minus 1, depending whether you're emitting or absorbing a photon. So you cannot ignore this term. An interband transition between two bands which have the same angular momentum will be forbidden, strictly speaking. You can go between an S-type band to a P-type band, from a P to a D, but you cannot go from S to an S or S to a D band, because you don't have you don't conserve momentum, since the photon takes away a unit h bar of angular momentum. So this is something that in optical transitions you have to account for. In principle, it can be calculated if you have any model that you choose. DFT, empirical pseudopotentials, maybe type binding in some approximations. K dot P, it's a little bit trickier. Type binding has to be DFT type binding. But in principle, if you know what the little u's are, what the periodic component of the block functions, then you can calculate the momentum matrix element for various bands, okay? And this is integrated over an entire cell. So you do the integration and you find this momentum matrix element. In principle, of course, I didn't write it down, but it depends on the K point at which you are. K and K prime, but again, we're taking vertical transition, so K and K prime are the same. And then the coefficient in front. So now we're ready to calculate the transition rates using Fermi-Golden rule. This is a time-dependent process, so using the term Fermi-Golden rule is appropriate. So we have the square of the matrix element. We have a delta, Dirac delta that expresses energy conservation, the 2 pi, the prefactor 2 pi over h bar, which comes from the in-time integration of your time-dependent, exponentially express the time dependence of the wave functions, and you have the usual coefficient that comes from the matrix element that you have squared. So for absorption, here we consider only absorption, so there will be an n over here, which comes from squaring the matrix element with the absorption, and then the momentum matrix element here. If you assume that the momentum matrix element doesn't change too much over the entire Brillouin zone, for example, for silicon, it's mainly dominated by whatever happens in vertical transitions with a gap of about 3 electron volts. Is not a terribly good approximation, but not terribly bad either. So if you assume that this is roughly constant, you can take it out, and it depends only on the band in which you're going. So it's approximately something. That depends on the integral. Think in terms of integrating over energy now by using the density of states. What you have is what's called the joint density of states, which is essentially what is the density of states simultaneously in a conduction band and in a valence band. If you're talking about absorption, you take an initial state, which is in a valence band, a final state in a conduction band. They both come with a density of states in their neighborhood, and they're connected by the energy, which is due to the energy of the photon that is being absorbed. So this is called the joint density of states at this energy. Okay, so it is not just the density of states of the conduction band or the valence band, but both of them simultaneously. This little j over here, which says joint. Okay, the rho usually denotes density, density of states, density matrices, that we'll see in the future. So essentially the absorption rate is proportional to the joint density of state. If this doesn't change too much, again, this depends on the polarizability. If this doesn't change too much, take it as a constant, maybe you can fit it empirically to experimental data. You see that if you plot the absorption rate, it will, remember, it will look very much like the joint density of states that you can calculate. And I'll show you the plot in a minute. Okay, so the total absorption rate can be written in this form. The spontaneous emission, so in that form, this is the spontaneous emission rate. If we want to deal also with the stimulated emission, we would have a term which is proportional to the n of q, as I did here. And you find that the emission rate depends now on the density of the final states, photon states that you can have. You can express actually even the electron phonon scattering rate in terms of the final density of phonons by doing a little bit of a transformation. It's up to you. It depends on which integral you do first. You do integral over k or over q. Here we decided to do the integral over q. You end up with the density of final photonic states that you can have. And again, it's proportional to this average momentum matrix element in a Brillouin zone. Again, this number is not something that you can calculate by hand. It's not easy to calculate. You can get a rough idea. It's going to be of the order of 1 over the lattice constant, so to speak, but multiplied by h bar. But it's something that you can calculate if you have DFT or whatever. It's the model to compute the band structure that you're using. This is the absorption, the spontaneous emission rate. The stimulator will be same thing, except that we have to integrate over the number of photons that we have. So here we'll have also the number of, or the density of photons that we're dealing with. In a laser will be the density of the photons that you have in a cavity, the electromagnetic cavity where the lasing action occurs, but it has the similar form. For example, you can calculate the absorption spectrum now by assuming taking this absorption rate and integrating over all of the states, initial states. If we assume that the crystal is intrinsic, the valence band is fully occupied, the conduction band is fully empty, ignoring at finite temperature a very small density of intrinsic carrier concentration that you have. In gallium arsenide, that's very tiny because the gap is quite large, it's about 1.4 eV at room temperature. So what we can do is approximate the emission, the matrix element for EM doesn't stand for emission, it stands for electromagnetic, for the absorption rate, and you integrate over the flux of photons that you have, okay, which is given by this n omega. It's the number of photons that are impinging on the system. You can express it in terms of flux with a suitable change of adding a few constants and so on. So you're integrating essentially the momentum matrix element. Let's take it as constant if you want. Now n and n prime, I fixed explicitly the valence as an initial state and conduction band as final state. You multiply by whatever is the polarization of light. If it's unpolarized, you just take the average over the two polarization states. The joint density of states that you have for a given frequency, photon frequency, the states, final states have to be empty. If the conduction band is fully empty, this is just 1, and the valence band has to be occupied because we want to absorb. If the valence band is full, this is 1. So these two factors become just 1 if you're assuming an ideal intrinsic semiconductor, and you have essentially the integral over the joint density of states at the frequency of the photons that are impinging on the system. And so this is the absorption spectrum, if you want, is given by this expression. Okay, let me show you, before going into excitons, let me show you, for example, the joint density of states. These are results that we've calculated using empirical pseudopotentials, which are the same. It's the same band structure that I showed here in this slide. So the same slide that we have also here for gallium arsenide, in this case. This is the joint density of states that you have. The absorption spectrum looks very much like it. So there is a sharp threshold for absorption. It's a direct gap material, so it's very sharp. It occurs roughly at the gap. And then it follows whatever is the density of final states that are available in the valence band and the conduction band in vertical transitions. This is very much like the absorption spectrum registered experimentally. And we did some calculations, for example, which are important for photovoltaics. If you take as the flux of the photons that you have here, so this number here, the solar spectrum at sea level, which has this funny designation. It's not a continuous spectrum, of course. It's not a black body. There are sharp absorption lines that depend, of course, on what wavelengths, which wavelengths are absorbed by molecules in the atmosphere. Anyway, if you integrate this over the absorption spectrum that you have, over the flux of photons that you have at sea level, and you get a distribution of electrons and holes that you can generate in a photovoltaic cell. And this is something that it is interesting to see, to decide, calculate the efficiency of the cell, the open circuit voltage, and so on, so the efficiency. This is for gallium arsenide. You have a very sharp absorption threshold at the gap. For silicon, you see that there is quite a sharp increase at the direct gap, which is about 3 electron volts, a little bit above 3 electron volts. And there is a very soft threshold, which extends all the way down. If this were in log scale, I was looking for it in the literature, you would see that there is a shoulder, a weak shoulder, which is temperature dependence. And these are phonon-assisted processes in which an electron jumps by 1 electron volt, by a gap, roughly the gap, to a virtual intermediate state, and then it emits or absorbs a phonon that brings it to the minimum of the conduction band over here. Oops. So this is a higher order process. It's clearly temperature dependent because you're relying on the assistance of a phonon to make it all the way to the minimum of the conduction, the minima, the 6 minima of the conduction band. So it's strongly temperature dependent, and it's weak because it's a higher order process. And that's why there is this little threshold over here. Another thing that is not seen here, in many cases you have a little blip, a little peak just before the gap. And this is caused by excitons. What you can have is, if you generate an electron hole pair across the gap, something similar to what we saw dealing with band gap narrowing, you have a Coulomb interaction between an electron and the hole, which has been left out in a valence band by this process. This Coulomb interaction in material in which the dielectric constant is small, so particularly in organic polymers and so on, they're used a lot in solar cells now to make cheap absorbing material. And in this case, you have to worry about this process. If the dielectric constant is small, then the binding energy that you have for this electron hole pair is essentially the hydrogen binding energy, the energy of ionization energy of the hydrogen. You may even have excited states, but the ground state has an energy which is given by this expression, where this is the reduced mass, depending on what is the effective mass of the electrons near the bottom of the conduction band and holes near the top of the valence band. So essentially it's a hydrogen atom, except that we're reduced to the center of mass frame, except that you have a mass which is corrected, and of course, most importantly, you have a dielectric constant which is quite different. Now, clearly the electric constant will not be vacuum. So 0 will be bigger than 1. For materials like gallium arsenide, germanium, silicon, this is bigger than 10. So the energy of the exciton, as we saw for the ionization energies of impurities, will be of the order of tens of millivolts, millielectron volts. So it's a small correction to the absorption threshold. However, and you see here where the peak comes in, and it's particularly important at low temperature. Okay, and you see this excitonic peak that you can see. So before reaching the direct threshold at, oops, where am I here? Touching the screen gives me strange things. Okay, so just before the direct transition, you see that actually the motion here in terms of EV is due to the fact that the band gap depends on temperature, and usually for all materials or semiconductors, the band gap decreases as the temperature increases. So this is just the reduction of the band gap. And you see that you have roughly a rigid shift, more or less, except that you have a peak which is more and more important as the temperature is reduced, because fewer of these excitons are ionized when their binding energy is compared to KT. In organic materials, this epsilon, that again is around 10 in semiconductors, 10 to 15, whatever, 16 for germanium, about 12 in gallium arsenide, 11 in silicon, and so on. In organic, it could be 2, 3, so the binding energy can be significantly higher. And then you have a peak which may be actually well separated for the absorption spectrum. So excitonic transitions are important. And again, when you talk about band gap, it is very important to distinguish between, as we saw discussing the band gap narrowing effect, between the electrical band gap, which is what you measure by exciting carriers above the gap, thermally in a non-radiative fashion, electrically by injecting carriers over some built-in potential, and optical instead, which is what you have by optical transitions. One correction, of course, that you might have is that the epsilon that you have to consider is different. In one case, electrical may be the static, and the optical will be, of course, the optical dielectric constant, so the high frequency. But the second effect that you may have, excitonic transitions, which reduce the threshold energy by the binding energy of the exciton. Okay, any questions so far? Everybody happy? Okay, then now let me move on. So we're changing gear here. We'll be now talking about something different. So far we've considered, I didn't jot down the entire outline of the class, but we've considered crystals at equilibrium, looking at their band structures. Then we looked at elementary excitations, the Schrödinger field, so describing electrons as excited state of the Schrödinger field. We've looked at phonons, we've looked at plasmons, we looked at the dielectric response of the system, and then we looked at interactions of electrons with excitations and impurities. So we've looked at various scattering processes, electron phonon, both the non-polar, the formation potential, and Harrison, polar, piezoelectric with acoustic phonons, and Fröhlich with longitudinal optical phonons. We've looked at some stranger situation, like the effect of the modes which are resulting from the coupling of the plasmon to the longitudinal optical phonon in a bulk material, and how the electrons interact with these modes, again in a polar material. We've looked at a similar problem, what happens at an interface. This can be extended and brought into the situations that were not discussed, scattering with the hybrid modes that exist at interface between a semiconductor and a polar insulator. We've looked at scattering with ionized impurities, electron-electron interactions, the long-range interaction, plasmons, and we talk about band gap narrowing as well, and short range. So just electron-electron interactions, which are viewed as fluctuations, short-range fluctuations of the mean field Hartree-Fock potential. And we'll look in particular what happens also when you have an electron in a conduction band interact with an electron in a valence band at sufficiently large energies of the primary electrons, exciting it across the gap, so impact ionization. We looked at something which is not really scattering per se with excitations of anything in a lattice, but the electron-photon interaction, which is the subject that we have just discussed. There are many other additional scattering processes, depending on the device structure that you have in mind, that may be considered, and we may discuss. One important effect, for example, is scattering with interface of linear roughness that you might have. Actually, this is one of the most important processes which are controlling the progress of the VLSI technology, ULSI, I should say, ultra large scale integration. And that's because scaling a device requires scaling not only in the horizontal direction, but also vertically, although with FinFETs it's not clear what vertical and horizontal mean anymore, but you have to make, to have very thin bodies. Silicon, including the insulator, the total dielectric thickness of the channel material and the insulator has to be small. Some fraction of the channel length depending on the scaling laws and the geometry they are considering. Double gate, nanowire, SOI, whatever. They all have a different constraint. All around gate nanowires, for example, are the best ones in terms of scaling. But thinning the body or making a narrow section nanowire increases the likelihood that your surface will be far from ideal. Will be vacancies, protrusion, diffusion of objects, other atoms in your at the interface, which will roughen the interface. Talking about nanoribbons, you may have instead the edges, which are roughened, so it's lineage roughness. This is actually, the interface roughness is actually what is controlling, limiting, if you wish, the transport properties of thin silicon layers. And that's why people are looking at alternative, such as two-dimensional materials. Although I think that the mobility and the transport properties of thin silicon still exceed what you can get from two-dimensional materials. But anyway, a lot of funding in this area. So this is something that we may talk about when we'll talk about electronic transport in low-dimensional materials, because it's a dominant process, very important. In principle, it's avoidable, unlike electron phonon, which you cannot get rid of. Even at zero temperature, you can emit. Interface roughness, it's something that ideally you may hope to control by growing the interface in a different way, by using atomic layer deposition, molecular beam epitaxy. Unfortunately, these are very slow and very expensive, so they're not amenable to mass production. But in principle, it's controllable, so there's always hope. We didn't talk about scattering with remote impurities. This is important in high electromobility transistors, for example. I mentioned the work that Brian Ridley did with this, his statistical screening model for impurity scattering to essentially merge in a smooth way the transition from the low energy the Brooks-Haring model to the high density Coleman-Laskov model in order to deal with scattering with impurities which are in a barrier layer where the electrons run in a channel, and so there is an interaction with impurities which are far away. In many cases, you may be controlled by neutral defects. For example, grain boundaries in amorphous material. This may be an important, it's not maybe, is the most important process. You may control by what it takes for an electron to cross a boundary, which we can view as a defect. Sometimes neutral, sometimes it's not neutral. Sometimes at grains you actually have dopant segregations. You may have defects which are actually charge states. So these are all processes that I haven't talked about, and they really depend on what structure you have in mind. I could probably add more. These are the most important ones that I could think of, and in particular this one, and we may talk about in the future. So now that we've looked at all of the scattering processes and these interactions, how do they determine charge transport? So we have to go and talk about how electrons move in a crystal in which we apply an electric field in a device in which the electric field may be non-uniform, in which we may have contacts, we may have boundaries, which will induce some of the scattering processes. We have dopants, so definitely we have interaction with ionized impurities. And of course, we have electrons by definitions, so we have electron-electron interaction. And of course, phonons were always around, so we will have to deal with the scattering processes. Electron photons will not be dwelling on it too much, but for optoelectronics and optical devices, clearly they're crucial. If you're interested in lasers, LEDs, clearly you have to worry about this. Okay. So this is going to be tough because it's a complicated issue. My main goal is to go from what's called the Liouville von Neumann equation, which is describe the dynamics of what is the equivalent of a distribution function in quantum mechanics, which is the density matrix. How the density matrix evolves in time according to quantum mechanics. And I want to go from here, we'll show what the equation looks like. I want to go to the semi-classical Boltzmann equation. The steps are tricky, and actually you cannot do it, strictly speaking. I wish I could. We will see that there is one important problem, which is the equation of motion for the density matrix is fully equivalent to a Schrödinger equation, or the Hamiltonian equation for the Schrödinger field, whatever you want to use, first or second quantization. It's time reversal symmetric, which means it's reversible. You can go backwards or forwards in time, and you cannot tell the difference. If you look at Schrödinger equation, as I showed before, if you take the time and flip it to minus time, you just get the complex conjugate of the equation, the equivalent. So, and again, the complex conjugate of the wave function has exactly the same physical meaning of the wave function itself. So you don't change anything. Devices get hot, as you know. Your laptop, your phone gets hot. And that's because the Boltzmann equation that describes, to a good approximation, transport in those systems, it's irreversible. If you flip the time from t to minus t, the equation changes completely. My clock, 1 hour in. So let me wait until it does its duty. Okay, good. So you cannot derive it. However, we can follow a procedure. You can find it in a few papers. There are not that many papers that do this thing. Specific about electron impurities, scattering, and electron phonon, they came out in the mid-50s from Latinger and Kohn, from Argyris, from Peter Price. But a general thing, I was trying to think about, okay, the name will come. Memory. The name will come, but somebody else who did this kind of analysis and study of how to proceed from quantum mechanics to semi-classical physics in various steps. So the quick outline is I will review a little bit classical statistical mechanics and a little bit of quantum mechanical statistical mechanics. So talking about what are distributions and what is the density matrix, I'll give you a couple of simple examples for spin state, just to remind you what the density matrix is. It's essentially a distribution. However, in quantum mechanics, you have to keep track also of linear superposition of states, amplitudes, and how they interfere. And so you need a little bit more than knowing which electrons you have at which position with which velocity. You also have to know what is the probability that the electron will be, the amplitude, I should say, that the electron will be in some linear superposition of states. We'll see what is the Liouville von Neumann equation for the density matrix rho. Rho, but from now on, will denote the density matrix, not the density, not crystal density, or whatever. Our goal will be to talk about the Boltzmann transport equation, so we'll tell you what it is, a brief history about how it was derived by Ludwig Boltzmann, will give you a reference, a wonderful reference, if you're interested in the history behind this. The project that Boltzmann had, which he's one of my idols. It's one of the major enterprises in physics I can think of. And then we'll go into a little bit of a different route, which is essentially the Boltzmann equation has what's called a collisional integral, the term that expresses what happens when electrons scatter among themselves or with anything else, our scattering processes. We want to derive that. And that has the form of what's called a master operator. Essentially describes the balance between in and out scattering between all the possible points in phase space. So we have to see when we can derive a collisional process, describe a collisional process with an operator of that form. And that requires going to the master equation. This was derived originally by Pauli. I will give you, I think it was 1931, so shortly after quantum mechanics was invented. And I will have to tell you a little bit about a wonderful paper by Leon van Hove, who used to be one of the directors at CERN, the accelerator in Geneva. But he wrote a wonderful paper in 1955, right around the years in which Latinger and Kohn and Argylis and Price and so on, they were working on deriving the Boltzmann equation. He has a more general picture about the onset of irreversibility and what it takes to describe collision via a master type operator, which extends the work of Pauli. So we will have to discuss a little bit this, and we'll follow a strategy which I'll describe here, starting with a closed system, introducing the reduced density matrix for the electrons and how its motion, its dynamic evolution is described, which is approach to equilibrium, which is what Pauli van Hove wanted to describe. We'll describe what type of interactions are of the Van Hove type, essentially most of the interactions that we've been dealing with. As long as you interact with something which has many degrees of freedom, or you average out the configurations, such as impurities, you introduce ignorance that way, then there are some good consequences of what you're doing. I mean, good because it simplifies the problem, bad because you're losing information. Then we'll open the system by adding contacts, and we'll see how we can derive a master equation. And we'll then use this expression, this derivation, to take the semi-classical limit and go to the Boltzmann transport equation. The master equation is a pet project of mine. It may be used for quantum transport in short devices. I may show you some results, but here it's a logical step. It's how to derive the master operator that describes collisions, the effect of collisions, which is what we have in the conventional right-hand side of the Boltzmann equation. And then we'll see, this will be done in the case of electron-phonon interaction. We'll see that you can do the same for impurity scattering, for electron-electron scattering, long and short range. I'm not sure we'll go into too much detail here because it's really painful. It's mainly an exercise in indices, keeping track of four body, 6 body, 8 body, 10 body processes essentially. So it's a little tricky, I should say, expectation values. So this is a way that we also introduced for quantum transport, but here I want to use the master operator per se in order to derive the collisional operator in the form that Boltzmann derived. The strategy will be a little strange. We start with a closed system, and so closed. We take a box, there are a bunch of energy levels there, we put electrons or whatever particles we have, stick to electrons to fixed ideas, and we'll set that t equals 0, we'll assume that they are off equilibrium. We have excited them somehow, optically, thermally, whatever, but with an electric bias. So they're off equilibrium. The system is closed. This is the type of system that Pauli and Van Hove consider. And then we'll see how the systems, which is in thermal contact with the bath, so it's interacting with another system which has a very large number of degrees of freedom. Clearly, this tells you something about the fact that we'll have to use statistical mechanics. We have many electrons, we have many degrees of freedom for the bath. We cannot tell the microscopic state of the system. Anyway, we cannot follow it, track it, or measure it, or observe it. So we have to do statistical mechanics, and that's where we have to review a little bit these concepts. And then we'll see how the electrons which are interacting with this bath, photons, the heat bath, how they decay or how the system evolves to equilibrium. Under which conditions in particular, we recover a sort of classical description, meaning that the off-diagonal elements of the density matrix, which are those that describe coherent linear superpositions of states, and we have to specify off-diagonal in which representation, of course, under which condition they die, or you can ignore them, which is the major contribution that Van Hove did. Pauli assumed at every time step that this happens. Van Hove says no. There are some situations and some conditions in which this is true in general. Having done that, we'll open the system, so we'll use a phenomenological description of what contacts do. They inject and absorb particles in some particular form. And then, having done that, we'll see that this is valid as long as the device of the structure, the system that we're considering, if you're dealing with electronic transport, is small, and we may say short in terms of its dimension along the transport direction. So it's a short system. This will be where we can define the interactions as described by a master type operator. And then we'll go to the semi-classical limit by slicing a long device, our 10 micron long device, slicing it into many small regions in each of which the master operator describes scattering, so that satisfies the Van Hove conditions, and we'll stitch them together and we'll recover the Boltzmann equation. It's a conceptually tricky process. From what I told you at the beginning, this is a time reversible equation. This is not where does the trick happen. Where does this happen? And this is where I think I will most disappoint you, because it will be just a stupid mathematical trick, a silly mathematical trick that really doesn't tell us much about what happens. It's what it's called the Van Hove limit. Completed the collisions. It's the same step that you take when in time-dependent perturbation theory, you look at what happens to the probability of a transition from an initial to a final state, and then you take the limit in integration of the time exponential that you have for the time dependence of the unperturbed eigenstates, and you take an integral all the way to infinity. So essentially you consider a completed collision, and you get the delta, the Dirac delta that expresses energy conservation. This is the step that introduces irreversibility. And if you wish, if you stick to the Copenhagen interpretation of quantum mechanics, indeed, this is where the collapse of the wave function happens. So it's no surprise that this is where irreversibility comes in. You had originally a system in a linear superposition of states. You had in the intermediate, as the collision evolves, the system which is in a linear superposition of many virtual states, but then at the end you collapse into one. And you cannot go back because you lose the information after the collapse of what was your state before the collapse. So these are different ways to express the same concept. Classically and quantum mechanically, there is a difference, of course. Boltzmann had the same problem in mind, essentially proving what's called the H theorem, as I will describe in a moment. Okay. Let's start describing the density matrix, then we'll take a break after we'll have discussed this, and we'll go into the Boltzmann equation, and we'll start our way through, our painful way, through the derivation of the Boltzmann equation. I think it's important to derive it, first of all, because it'll give you an idea what quantum transport would entail, and what semi-classical transport assumes, what sort of simplifications or conditions that you're assuming in semi-classical transport. I want to mention just one thing. You notice that I talk about the density matrix. Strictly speaking, this is not the most general quantity that you want to talk about. A density matrix is essentially the expectation, the thermal expectation value, or the ensemble average, thermal ensemble average of the Schrödinger field, and actually of two Schrödinger fields, of the density. So the psi dagger psi, which is the psi star psi is the density in quantum mechanics. This is the density in second quantized form. Of course, the psi dagger and psi depends on position and time, r and t and r prime t prime. The density matrix assumes that you're taking the product of psi dagger psi at the same times, two different positions, r prime and r, but at the same time. In principle, you can take it at different times. This is a Green's function. So you go into what is called the Green's function method, or since we're dealing with non-equilibrium, the non-equilibrium Green's function method. I think it's fair to say that people still disagree on what you gain by moving from the density matrix to the Green's function. So by considering the field-field correlation function at two different times. I don't have a proof, I don't have an answer, I have the feeling that you don't gain anything, and you just complicate the picture. It's usually said that with the Green's function you have information about the spectrum, but if I decompose or express my density matrix in the representation of the eigenvalues or the eigenstates of the unperturbed Hamiltonian, I also have a spectral representation of a sort. So anyway, I'm open to disagreement and stand to be corrected, but this is an ongoing controversy, and the density matrix people and the non-equilibrium function people seem to follow a different path. Ultimately, it's funny that systems of equations that you end up to solve is very similar. Okay, so statistical mechanics. So far, everything we've said is on pure states. We have talked about the crystal in its ground state. We look at the band structure, even looking at elementary excitations. We looked at excitations as excited states or harmonic oscillators in second quantized form. So the presence of a phonon means there is a phonon with a wave vector q and polarization eta, means there is a harmonic oscillator q eta labeled by these numbers, and in its ground state there is no phonon. In its first excited state you have one phonon, and so on. Since they're bosons, we can build up as many phonons as we want by filling the excited states of the system, of this harmonic oscillator. But these are pure states. Even in second quantized form, yes, we deal with many body, but we know everything about everything. We know exactly what the Hamiltonian is, we know exactly what the eigenstates are, the eigenvalues are, and so on. Now, in the real world, we know very well that this is not what we can achieve. If you want to study a gas, that's a typical story. We cannot tell what is the velocity and the position of every single molecule, even classically, so ignoring Heisenberg's uncertainty principle. What is the position and velocity of every molecule in a macroscopic volume of the gas, in a room, in a tank, in a bottle, whatever. So we have to do some averaging. So there is the onset of a concept of probability, which is different from the probability, the term as it's used in quantum mechanics. In quantum mechanics, if you believe in the Copenhagen interpretation, which I do, then probability has a specific meaning related to the interpretation of the measurement, of the collapse, and so on. What is the probability that the system will collapse into a particular eigenstate of an operator as given by the dot product, or the square of the dot product of the initial state over the that particular eigenstate of the observable that you want to measure. Here, the probability that we introduce is a classical probability. The quantum mechanical probabilities, we know that it's weird. I don't want to go into the Bell inequalities and Bell theorems, but it has some strange properties. The probability that we're dealing here in statistical mechanics is the usual probability. And so rather than describing the system as this is my system, these are all its canonical coordinates or canonically conjugated momenta, as many as they might be, 3n, n is the number of particles, so 10 to the 23rd for a particular chunk of some microscopic material. What we do instead is assume that we have a very large, infinitely many actually, identical replicas of the system, but each replica is in principle in a different microscopic state. This is the state that I don't know, in which each particular element of the ensemble is. They are prepared all identically from a macroscopic point of view. They have the same macroscopic properties, but the microstate in which they're all different. And I don't know what they are. So we have to move to a situation in which to describe the world with statistical mechanics. This idea was developed, I think, in our context originally by Maxwell, then by probably who was the first great American physicist, Gibbs, and then, of course, by Boltzmann, and we'll discuss it a bit more. And then, of course, quantum statistical mechanics had to wait until, well, even before quantum mechanics actually was invented, because we saw the Einstein's coefficient, for example. Black body spectrum was at the beginning of the 20th century, so some 2.5 decades before quantum mechanics was invented. Boltzmann, as I will mention, had in mind an ambitious program of explaining thermodynamics with statistical mechanics in the classical world. He died before atoms had been accepted as existing, at least by physicists. Chemists already accepted them. Physicists hadn't accepted them yet. Anyway, so we're talking about statistical ensembles. So instead of considering, for example, a single state, we consider a large collection of n as a large number of identical prepared copies of our original chunk of semiconductor, for example. And instead of specifying the state by a particular wave function psi alpha, we simply say what is the probability that the system will be in that state, which means how many of these n ensembles and replicas on the ensemble are in that particular state. And this is what we call the distribution function, or in some sense also a density matrix. So we will talk about a probability of finding a system in a state alpha as given by the number of replicas in the ensemble, little n sub alpha, divided by the total number that we have of state in that particular state. Okay. Now, there is a difference between classical mechanics, so distribution function, and quantum mechanics. This is all relatively trivial stuff about classical probability theory. Suppose that I have a particular observable Q that can take big Q, which may be my position, coordinates, angular momentum, whatever is the variable that I'm determined to have. And I want to find the average of this object. In order to find it, I have to know what is the probability, the probability distribution of that variable little q being in a particular state Q. This is essentially the number of replicas in my ensemble that have a particular value Q over the total number of states. So clearly the average will be the usual average. What is the probability of having a particular value little q? I multiply by the little value q, I add them all, and this is, if you want, is a weighted average, weighted by the probability distribution. We can convert it into an integral over all the variables, or the particular variables q. And the distribution functions also determines the average of all of the powers of q. So this is a detail that I will not have to deal with too much. So again, in classical probability, you define a probability distribution, probability density, whatever, as which is suitably normalized to 1, which tells you what is the probability that given a particular position of the particle in a box, the particle will have that particular position. And in physics, statistical mechanics, we can view it as replicating 1,000,000 times the same box and looking at how many boxes we have over the total in which we find the particle at that particular position. Okay, so this is roughly what the distribution function looks like. In quantum mechanics, we need a little bit more. As I said, this doesn't tell us anything about the probability that our particle will be in a linear superposition of two positions. It will be in a packet, for example, a wave packet, in which the position is not fixed, in which this probability distribution now will be given by the square of the wave function, spatial dependent wave function. Okay, so there is something missing in conventional probability, and that's why we need the density matrix. So the density matrix is basically viewed in this way. I should add a time, and this is just the expectation value over my ensemble. So I replicate my electron in a box 1,000,000 times. I look at the wave function of the electrons, or in second quantized form, at the Schrödinger field that describes the electron in that box. And I take the average of the product between the psi dagger and psi. This evaluated at a different position than this one. At the same time, though, I didn't write it. I should have written it down, actually. If I take it at two different times, then the object that I have here depends on x prime, t, and t prime. And this is actually Green's function. It's called the Green's function because actually it is the Green's function of the differential equation that describes the dynamics of the system. Okay. In terms of the expectation value of rho, so in terms of this density matrix, we can write the expectation value of a quantity. That again, this expectation value is what we have in conventional quantum mechanics. We just take the sandwich of my observable Q. I would have to put a hat here, meaning it's an operator if I work in first quantization, and I take the diagonal matrix element of this object, right? Okay, I can write it clearly in terms of integral of Q psi star psi, if I go to conventional quantum mechanics, which is essentially what I wrote here. And this can be written in terms of the trace of an operator. Again, between operator and matrix, I have to make a slight distinction, or it will be apparent in a minute. So I multiply this matrix in a given representation times the observable in the same representation. This is a position representation. You see that it's a trace because I'm integrating over x and x prime at the same x and x prime. So it's a trace of the product between the density matrix and the observable. Is very similar to what we have here. Essentially, what I'm doing is I take the variable that whose expectation value, or its average, statistical ensemble average I want to calculate, I multiply by probability distribution. Okay, here I also have to account for the possibility that the system will be in a linear superposition of any two states, any possible combination of any two states. So now, rather than having a diagonal, view this as a diagonal matrix with Q only the diagonal element and P of Q only the diagonal element, I need information about the off-diagonal elements. What is the probability the system will be in a linear superposition of two states? X prime will be in a simultaneously an x and x prime, which is something that you can have in a wave packet, for example. Okay, so this is essentially the same object, okay, that we have in classical mechanics, but I need to add a dimension, so to speak. And so instead of a probability distribution function, which is a scalar function, I need to talk about a matrix. I think I need a little break because my throat is hurting, so we'll take the usual 5-minute break. 10:26 here, so let's take a 5-6 minutes break. Okay, a little bit longer. I need to take a coffee and warm up my throat, and then we'll continue, and I have to give you a little bit of a detail about some properties of the density matrix. But roughly, I hope this makes it clear. what I need is a non-diagonal elements. Here I have a P of Q. Here, oh, come on. Here I need a row of XX prime of QQ prime, whatever you want to call it, because I want to be able to express the correlation that I might have, or the amplitude that I might have for the system to be in a linear superposition of states belonging to the two different eigenvalues of the observable Q. Okay, and so I need to go from a scalar to a matrix. This is obvious why I call it a matrix, although it's a non-local operator here. When why it's not, I don't call it an operator, will be clear by its time evolution. It's a detail, it's a nit about terminology. Okay, any questions so far? If not, let's take our little break. And am I still online, by the way? Do I still exist? Yes, no?
Yes, you do.
Yes, you do. I exist. I'm so happy. Okay.
You
All right.
exist and unique.
I exist. I'm not unique. Well, that's up to a mathematician to decide. The proof of existence we have. Uniqueness, I don't know. In some parallel universe, there may be another me, right? So, all right. I'll see you in 6 minutes. Okay, are we back online? Everybody?
Yes, we are.
Good. Okay. Just one comment that I thought about. Here I use the position, so to speak, as independent variable. If we Fourier transform, for example, these objects, view them as simple wave functions now. For example, I can expand them into a sum of the eigenstates of the Hamiltonian that I'm dealing with. Then we can talk about a density matrix represented now in the basis of the eigenstates of the Hamiltonian. So the variable x and x prime would be replaced by energy and energy prime, for example, or momentum k and k prime. So we can talk about the density matrix as representing the system. Well, it's an ensemble average of a collection of system that tells me in the diagonal terms k equals to k prime, what is the probability of finding the system in that particular eigenstate of the Hamiltonian. And the off-diagonal elements, k prime, will give me an idea about the amplitude, tell me about the amplitude of the system being in a linear superposition of two states, k and k prime. So for an eigenpacket, which is constituted by many wave vectors, if it is sufficiently localized in space, there will be plenty of off-diagonal elements because there will be a significantly large amplitude of any k with any other k prime in a domain, in a support of the packet in k space, for example. And in order to take the average, all I have to do is, of any observable Q, I have to take my density operator, multiply by the operator associated with that observable, and then take the trace over whatever representation I have. A trace over positions, as I have here, a trace over k space, over k vectors, if I want to go into Fourier transforms, and so on. So the basic object that describes everything about the system now is this quantity, this object here. I put a hat because now it's an operator. Between this and the conventional operators, the Hermitian operators that we associate with observables in conventional quantum mechanics, there is a big difference that I will mention in a minute. This operator here, let's call it operator for now, has very interesting properties, which I kind of chopped off. I put them too low in a slide. It's Hermitian, so it's a good operator. The eigenvalues are real eigenvalues. The trace of this, since the wave function is normalized to 1, you realize that the trace of this object is just the integral of the square magnitude of the wave function, which is normalized to 1. So this is normalized to 1. The square of taking the product of rho by itself gives me the identity operator, gives me the operator itself with a plus or minus sign. That depends on, since I have to do a commutation or an anti-commutation of this field, depending on whether this field describes fermions or bosons, taking the square of this object, I obtain the same object with a plus or minus sign, depending on whether flipping the position of two electrons gives me a symmetric operator, a symmetric wave function, which is plus, or it's associated with an antisymmetric object, which is what we have for fermions. So the density matrix contains Pauli's principle, or the spin statistics theorem already, because the canonical commutation or anti-commutation rules are implied as being obeyed by these field operators. Examples. The typical example that we have, which is analogous to the distribution function in classical mechanics, let's consider an electron, and the electron has two available spin states, up or down, plus or minus, along the conventional z-axis. If we have a density matrix given by this, the trace of the matrix is 1, so the total probability of finding the electron in any spin is 1. Notice that the off-diagonal elements are 0. It means that the system actually is in a totally unpolarized state. It's representing, if you want, a flux of electrons with 50% of the electrons spin up, 50% to spin down. I do not know which particular electron has which particular spin. All I know, this is my statistical ignorance, is that it's 50-50, okay? The density matrix expressed this way instead, so this defines an impure state, okay? It's not that the system is, the electrons are in a linear superposition of spin up and spin down state. It's different. We'll discuss it in a minute. This simply tells me that all of the electrons are in a particular spin state, but the probability of having spin up or spin down is given by 50% in each case. So it's an impure state. The density matrix represented here instead tells me that all electrons are spin up. So this is a pure state. It's a trivial situation, okay? All electrons are spin up. So this is a probability which is not related to an amplitude. It's not the square of an amplitude. This is simply describing the fact that I do not know exactly which electrons is which spin. All I know is the distribution that they have, which is 50-50. This matrix, this density matrix, is a different object. If I consider now electrons which are in a linear superposition of spin up and spin down, which is not what I had before, this is different. This is not the classical world anymore. We cannot have, in classical mechanics, a linear superposition of states. The state of a system is either this or that. It cannot be a combination of the two. Instead, in quantum mechanics, of course, the superposition principle actually is where Dirac started from in his book, Principle of Quantum Mechanics. He starts from the superposition principle to, quote unquote, derive quantum mechanics, okay, and the Schrödinger equation. So in this case, if I form the density matrix out of these states, spin up these two states as a starist, I get this expression. This now has diagonal terms, which tell me what is the probability of finding a state in a given spin state, but also has off-diagonal states, which tell me that there is an equal probability of finding a system is a linear superposition or spin up down or spin down up states, which are the same because of the way I've described it. If I had to put a minus sign here, I would have to a minus sign in one of the off-diagonal elements. So this describes the amplitude, these off-diagonal states, the amplitude of the system being in a particular state. The probability will be the square of that. So it's something which goes beyond statistical mechanics. Okay. Any question about this? This is all I'm going to say about what is the density matrix. Again, it's an extension of the concept of a probability distribution that we have in classical mechanics, which is, again, how many replicas of my ensemble are in a particular microstate, and this gives me the particular probability of finding the system in a microstate. In quantum mechanics, we have to extend that in order to account for the possibility that the system is in a linear superposition of two microstates. Okay. How does it evolve in time? It's quite trivial. Regardless of whether you view this as a first quantized Schrödinger equation or a classical field in second quantization, so whether you want to put a star or a dagger here, it doesn't matter. You can multiply this equation by psi star on the right. You can multiply it on the left. You can becomes a conjugate. You can subtract the two, and at the end you find that the difference between the two operations that you have done is given by this, which simply says that the commutator of the Hamiltonian with the density matrix, as you see here, is equal to the time derivative of the density matrix itself, multiplied by h bar. This is the major difference that we have between operators and the density matrix. For operators, the Heisenberg equation of motion for the operators differ in two respects. First, the order of the Hamiltonian and the operator are swapped. I write it here. Okay, the Hamiltonian comes later if you put a plus over here. So the equation of motion is similar, but there is a sign difference, the order in which the Hamiltonian comes in. Who cares, you say? Well, yeah, that's perhaps a detail. It's a minus sign. The major difference instead is the following. The density matrix is defined as the product of two wave functions or two fields, okay? The field and its complex conjugate or its Hermitian conjugate in second quantization. The wave function evolves in time in a Schrödinger representation. It's fixed in a Heisenberg representation. So the density matrix evolves in time in a Schrödinger representation. It's fixed in a Heisenberg representation. It's exactly the opposite of what operators do, observables do. That's why I like to call it matrix. Yeah, mathematically speaking, it's an operator acting on the Hilbert space of your system in first quantized form, on the Fock space of your system in second quantized form. So it is an operator. Hermitian, it's a good operator. But its time evolution is it's the opposite of, in terms of which interaction, in which representation you use, the opposite of what you have for the conventional operators, the observables. Okay, so these are the two reasons why I rather call it a matrix rather than an operator. Although in somebody calls the matrix density operator, that's fine. I mean, it's if you want its terminology, but using the term matrix reminds me that there is this difference, and we're going to use it because we're going to use an interaction picture now. An interaction picture, the states evolve in time according to the perturbing Hamiltonian. Instead, the operators evolve in time according to the free Hamiltonian, the non-interaction Hamiltonian. So this is a big difference that we will use and we have to keep in mind. By the way, this is called the Liouville-von Neumann equation. I'll tell you a little bit why Liouville and why von Neumann. Okay, a little bit of fun here in historical perspective about the Boltzmann equation. Our goal, so I'll start setting up where we want to go. We want to go from here to here. This is a classical distribution function. This is, as I will discuss in a minute in the next slide, this is the equation that Boltzmann wrote, except that he used the variable velocity rather than wave vector. Quantum mechanics had not been invented by a little bit, by a couple, 3 decades when he died, 2 decades when he died. So this is the probability of finding a particle at position r and wave vector k in phase space. So what I'm showing here is the phase space. This is a 3-dimensional real space. For obvious reason, I cannot draw a 6-dimensional space. This picture actually was generated by my former colleague and still dear friend, Dr. Steve Locks, when I was at IBM. And it describes the evolution in time of the probability of finding a particle, so say, at position r and k at time t as a function of time. And I will show it in a minute how to derive it. It depends on something quite trivial, mathematically, not so trivial physically. It's Liouville's theorem in classical statistical mechanics. It says that particles can move around driven by the external forces. This is the derivative of the momentum with respect to time. So it's the external force that acts on a particle. They can diffuse, so this is usually called the drift term. They can diffuse in real space. They move around, they have a velocity, so a particle which is at a particular point r can move around this axis, which is 3-dimensional real space, by diffusing, and can drift in k space under the application of a force. And in addition, they can jump from one state to another, from one k to another, vertically. They can move to another position in some fictitious collisions, according to some term that we have to find what it is. This is the term which is called the collisional term. It's the time evolution given by collisions, which are in and out. You can scatter in a k space, a k point, or out of a k point, depending on whether particles at a k point will scatter in, or particles at this particular k point can scatter out. Historically, this was due to Ludwig Boltzmann. This is a picture, I think it's an early photograph of Boltzmann when he was relatively young. The history of Boltzmann life, a scientific history of Boltzmann life, has been given by a wonderful book that I encourage you to read if you're not ready yet. It's fantastic. It's been written by Carlo Cercignani, who unfortunately passed away, I think in 2004, I think, I'm not sure. Actually, I took a class with him when I was in Milan about the Boltzmann equation, and I bumped into him at some conference decades later, getting out of the hotel where we were in Toulouse, and I told him, you may not remember me, but I was in class when he gave that course years ago, and we had a nice chat. So he wrote this wonderful book, which is it's a strange book. It's a biography which you can read before going to bed, but there are some chapters which are really physics intensive and math intensive. So it's not a conventional biography. Carlo, by the way, was one of the few mathematicians, mathematical physicist, we may say, with an international reputation. He's one of the few whose work, mathematical work, was translated into Russian, which is something, given the high level of mathematical skills that is diffused in Russian school. And here, okay, I don't know whether this is a portrait or whatever of Joseph Louisville, and I will mention his theorem in a moment. And this is John von Neumann, who we all know is one of the main characters who contributed to the interpretation of quantum mechanics, the famous von Neumann chain, and how he thought that he could solve the problem. He actually didn't, very much like Boltzmann that thought he had solved and proven the H theorem, showing where irreversibility comes from. He actually didn't. And Liouville, okay, that he lived in 1800s. This is the source of the pictures. Okay, so the Boltzmann equation is where we want to get to. Here I left the collisional integral unspecified. The form, it's not really what Boltzmann did. Boltzmann really talked about the gas. His major goal was to prove thermodynamics, derive the laws of thermodynamics from the laws of dynamics, classical mechanics, Newton's laws. This is a sentence that it's very important, assuming that atoms exist, and indeed the title of the book here is The Man Who Trusted Atoms. In Italian is The Man Who Believed in Atoms, I think, the more literal translation. When Ludwig Boltzmann was working on his goal of proving essentially the second law of thermodynamics. The first law is kind of a given, is energy conservation. The second law is the tricky one. The third law did not exist at the time since quantum mechanics was not there. But the second law is tricky because it represents the onset of irreversibility. Entropy grows, it never decreases in a closed system. So in order to prove it, you really have to prove what is called the H theorem, which essentially shows where the system goes from reversible to irreversible in time, which is something that they showed. And he was dealing with gases. He thought he proved it, having found an equation which has essentially this form. And actually, his problems that led him to suicide, in addition to other issues, stem from the fact that Ernst Mach was a big boss in German physics at the time, did not believe that atoms exist. Well, let me correct the statement. Did not think that the assumption that atoms exist was really necessary. It's a strange thing that I think from the time of Lavoisier, chemists realized that chemical reactions can be explained if you quantize matter, if you assume that every element interacts with other elements in discrete chunks. So in some sort, they believed in atoms. I think I mentioned Augustus Kekulé's result on aromatic compounds, dealing with graphene and graphene nanoribbons, talking about the chromatic structure of graphene nanoribbons. Chemists already describe aromatic compounds drawing down hexagons of the carbon sextets. So assuming that carbon atoms do exist. Physicists were more reluctant. They really wanted to more reluctant to accept the idea They wanted to see some direct evidence. This was provided essentially by one of the three fundamental pieces of work that Einstein published in 1905, and that's Brownian motion. In 1905, he published the three famous papers, one on special relativity, another one on the photoelectric effect, for which he got the Nobel Prize some 20 years later, 1927, I believe. Correct me if I'm wrong. And the third one was on Brownian motion, explaining diffusion, Fick's law, if you want, diffusion by the thermal bumps that a molecule in water gets from the other molecule. So showing directly that atoms do exist. This was in 1905. I don't remember the exact year in which Boltzmann killed himself. It was 2-3 years earlier. He killed himself in an Italian resort town of near Trieste, Duino, I think, and he hung himself on a chandelier of the hotel room when his wife and daughter were out shopping. He was plagued by losing eyesight, very strong migraines, persisting migraines, and also he was terribly aggravated by the criticism that Mach had raised about the fact that the Boltzmann equation doesn't prove H theorem because it assumes it. So the Boltzmann equation is this way. First of all, let's start with Liouville's theorem. Take this distribution function, which is, as I said, depending on how you normalize it, the probability of finding a particle at position r at wave vector k or velocity v, if we're dealing with real space, at position t. If we follow the trajectory of the evolution, of this distribution function, following the trajectory of the particle, we get a constant, because we just keep what is the probability of finding a particle here, but here in phase space means along the trajectory in which the particle is moving. So the total derivative of this object is 0. Using the chain rule, you can write the total derivative as the partial derivative of the probability if it has any explicit dependence on time, which we will largely ignore in the future, and then the derivative of the position with respect to time, dotted with the gradient. That's just the chain rule of derivatives, the gradient of the function with respect to position, and the same over velocities. Again, k and v, replace it here if you wish. For parabolic bands in a solid, the velocity will be h bar k over m, so it's just a constant. Of course, it will be the group velocity if we're dealing with a more complicated band structure. And then we have the derivative of the velocity times the gradient in velocity space of the distribution function. And this has to be equal to 0. So this is Liouville's theorem of classical mechanics. This is true if the particle doesn't jump out of a k point to another k point all of a sudden due to collision. So this is true if there are no scattering events, if there is no interaction of particles among themselves or whatever. So the idea that Boltzmann had to chase was to see what happens to this mysterious piece, the collisional term. And he wrote it this way, simplified in the case of interaction of particles not among themselves. That's more complicated. This is a simpler case of a classical system in which something, phonons, talking about semi-classical because I'm ignoring the Degeneracy and Pauli's principle here in this expression. These represent the probability per unit time that a particle at position k prime in k space jumps to a position k. So it's a scattering probability, but limited to a particular initial state and final state. In general, I write the final state before the initial state. I'm not sure where I got this habit. And this is the same, but flipping the two processes. So the total derivative in which the function goes, adding the collisional integral and bringing this partial derivative on the other side, you get the minus this term. This is the velocity, which is for our electrons in solid is just the expression for the group velocity of the electrons. The force, which is the dV/dt, which is essentially the change in momentum, which is if we have an external electrostatic potential, this is just the field minus the field that is driving the charged particles. This is just Liouville's theorem. This will be equal to 0 from this. However, we add a piece. And the piece says that at a given position in phase space t, the distribution function can change in time because of particles which are in another position in k space k prime can scatter into k, plus sign, or a minus sign, the particle which is at k scatters out to a position k prime. Okay, so this is what I will call the master operator. It's a master form. It simply is if you want, it's a balance. It's an off-equilibrium balance. So it's not detailed balance at equilibrium, but it says that the total change of the probability of going from one point k to a point k prime is given by this expression. It's you can increase the probability of the number of particles at k point k, or the probability, depending on how you normalize f to 1 or to the density, is given by the collisional process that are described by these terms. What is the problem? Notice that if I change t to minus t, I change the sign. So it's not like Newton's law where I change time to minus time. Since I get a second derivative, nothing changes. Here I have first derivative. So things change completely. The past and the future are clearly labeled by what is the sign that I have in front of the time derivative. Boltzmann thought that having derived the equation of the collisional integral, oh boy, we're to 11 clocks here. Sorry about that. It keeps me company at night. Okay, so he thought that he had proven the H theorem because we're going from Newton's law, which are essentially given by the dV/dt, by this term, okay? Newton's law gives you something which is now irreversible in time. The problem is that, as Mach pointed out, there is an assumption made here implicitly in writing the collisional integral this way. It has an intuitive form, an intuitive interpretation. What's wrong with it? Clearly, I have a position, a particle at position r. It has some wave vector or velocity, k prime or v prime, and this is the probability will go into another velocity or another k vector. In and out processes. So perfectly reasonable. The problem is that these objects do not depend on time, do not have any memory of where the particle is coming from. If you think quantum mechanically now, it's a simple way. If you think about what we discuss in terms of impurity scattering between with a second impurity after an electron is scattered with the first impurity. We took essentially the same approximation that Boltzmann made of saying that the cross-section for scattering with the second impurity is identical to the cross-section of scattering with the first impurity. But it is not so, because the wave function that hits, of course, Boltzmann didn't know about wave function, I'm using a quantum mechanical analogy, but the wave function that hits the second impurity is given by the superposition of the incident wave and the wave which is scattered by the first impurity. So they are not the same. The scattering cross-section with the second impurity depends on what happened before to that particle. So there has to be an integral over past times from minus infinity to t over t prime of some dependence on t prime here and here in a distribution function, which is indeed what we will derive as an intermediate step, what is called the pre-master equation or the pre-master form of the scattering operator by Zwanzig. So this is one of the causes that drove Boltzmann to suicide, unfortunately. This kernel and the distribution function itself does not remember the past history of the particle. Clearly, erasing the past sets immediately a preferred direction for the arrow time. The past is now different from the future because we're going to predict the future, but we don't know the past, we're going to go back. And this is the reason why this equation is irreversible. The basic thing is that, as far as I know, the H theorem remains to be proven, or to put it in another way, there are lots of proofs. which means that none of them is correct. So we cannot derive this equation, strictly speaking. Derived, put it in quotes if you want, and put it in italic here. We can follow a procedure to actually that will lead to this equation, but we need some approximations, and some of them are not terribly clear. They're mathematically obvious, particularly one, as I told you, the completed collision, the Van Hove limit, but what they mean physically, it's a little fuzzy. So in addition, irreversibility and the arrow time, there's plenty of books that you can read. It's a very challenging problem, very, very, very intriguing. Time has a different meaning and irreversibility has a different meaning depending on whom you talk to. In thermodynamics, it has a meaning. In quantum mechanics, it has a different meaning because of the collapse. So the interpretation of quantum mechanics has something to say about what you mean by irreversibility, measurement theory. The measurement theory, the Copenhagen interpretation of quantum mechanics requires an observer, which is the cause of all paradoxes and the von Neumann chain. A subsystem which is described quantum mechanically is measured by a classical system, but what is the distinction between the two? The classical system actually should also be described by quantum mechanics. So when you make a measurement, the measurement system and the system which is measured are also in a linear superposition of states. You need a third system that measures the first measuring system and the system itself, and so on ad infinitum. So this is one set. If you're talking to a cosmologist, they're dealing with the universe. There's no external observer in the universe. So how do you change the interpretation, the Copenhagen interpretation of a measurement in a universe where there is no measuring apparatus? Everything is part of the universe. So there we go into a different concept of irreversibility, and there we go into the incoherent trajectories, the omnibus interpretation of quantum mechanics, which is what using path integral quantization techniques, what people in quantum gravity and cosmology do. So it's a challenging problem. I don't have a solution, of course. I wish I had. So we'll go and now and try and derive this equation starting from the Liouville von Neumann. So again, we're starting from here. That's our starting point. And then we'll try and see how we can get to this point. What is our strategy? Tragedy, actually, because it will be extremely painful here. So bear with me. So let's start simple. Let's consider an homogeneous system. So pick a box in which you have some semiconductor, there is a bias applied, but the system is closed. And at time equals 0, think about one of the contacts being temporarily open, injecting electrons, hot electrons, into our system. They occupy some high energy states. They're equilibrium in the source, say, but clearly they will be off equilibrium when you move across the device toward the drain. But having introduced these hot electrons, off equilibrium electrons, we close the doors, and the system does not interact with the outside environment directly by exchanging particles. So essentially we go from a grand canonical to a canonical statistical mechanics ensemble. It's not interacting with the contacts, particles are not exchanged for now, but the system interacts with the thermal bath, with phonons, and we'll explicitly consider the electron phonon Hamiltonian. Okay, so this is the system that we will consider at t equals 0. We will further consider already that the electrons and the phonons, as I introduced these electrons at first, they are decoupled. So I have first at t equals 0 minus, I have the system empty with phonons at equilibrium surrounding the system, this thermal bath. Then I open for a very short time a pulse delta t, one of the contacts, I inject these electrons. I close the doors of the contact immediately, and the electrons are still in a distribution which is whatever was injected from the contact that I'm assuming at equilibrium, but they're hot because there is a bias applied in the device. So think about a bias like this, and I'm injecting hot electrons from one side. We will write the Liouville von Neumann equation for the time evolution of this system, this closed system. We will actually simplify the description by saying, I really do not care about phonons. I will actually assume a Markov approximation for the phonons, so I don't remember where the phonons are coming from and where they're going. So essentially, I will take a trace out of the thermal occupation of phonons, the equilibrium density matrix for the phonons, or my entire density matrix that depends on the electron coordinates and on the phonon coordinates. So I'll get rid of the phonon coordinates by averaging out over their equilibrium distribution. This will lead me to consider only what we call the reduced electronic density matrix. And people usually say that I trace out the irrelevant degrees of freedom. Irrelevant not because they don't matter, but because I don't want to study them. Rather than I don't want. I don't know how to. Let's put it differently. Therefore, I decided I don't care because I don't know how to deal with them. Okay, the fox and the grapes. Then we will consider the Liouville von Neumann equation, as I said, in interaction picture, so that my density matrix evolves in time only according to the electron phonon Hamiltonian, my interaction Hamiltonian. The operators evolve in time according to the free Hamiltonian that includes already the potential, by the way. I will have to step away from that in order to derive the Boltzmann equation, but for now, we'll consider eigenstates of the system, including the potential. We will integrate in time the Liouville von Neumann equation by iterations, and we'll consider only the leading terms, which will be a second order term, in the strength of the interaction, the electron phonon interaction. Now the tricky part comes in. Now we have to use Van Hoff argument, that I will describe in a moment, to say that we can ignore off-diagonal elements of the density matrix as long as the chunk that I'm considering is short, meaning that the mean free path for these electrons is longer compared to the size of my device. Or if you wish, if I inject pure plane waves. I will tell you a little bit how Van Hoff formulated this in an elegant way. And this will lead us to something which will begin to look like the master form of the collisional integral in the Boltzmann equation, except that I will still retain reversibility in time. The pre-master equation, there will be an integration over past times that I have to do over this term. So there will be not just a sum of k prime, there will be an integral from -infinity to t of whatever happens inside here. So these objects will depend on time, actually, on the past time, which is what we said is the Stotz-Hallen-Satz or molecular chaos assumption that Boltzmann did. We will not do it exactly the same way, but we will use the Van Hoff limit to get that. Before doing that, we will open the system now. So we will open the doors and say, okay, now that we know how the system goes to equilibrium when it's closed, when there are no particles exchanged between the system and the various contacts, source, drain, whatever you have, substrate, gate, whatever. Now we will open the system. We'll use some phenomenological model to describe how the contacts attempt to retain charge neutrality regarding the states that they are injecting. And having done that, we will now take the limit, which is called the Van Hoff limit, essentially the same limit that you take to get Fermi-Golden rule. So we'll take the limit of alpha squared t, where alpha is the dimensionless coupling constant with the phonons or whatever interaction you're considering. We take the product alpha squared t as a constant, take t going to infinity, and alpha squared on alpha goes to 0 at the same rate. And this is what is called the Van Hoff limit of completed collisions. Okay, and this finally will give us the master equation. This is the tricky part. Mathematically, it's pretty clear how to do it. It's related to the way you handle the Kramers-Koenig relationship, for example, that we discussed, dealing with how you get the delta function and the principal, Cauchy principal part of an integral when we were dealing with the dielectric response of a system in a non-degenerate limit, and I give you the expression in terms of the plasma dispersion function. It's exactly the same step. It's just a regularization that we make in order to make the integral converge. And this regularization is a mathematical trick, but it is the one and only element that introduces an asymmetry between t and minus t. Disappointing, because it doesn't tell us much. Yeah, I mean, you can justify this turning on interaction adiabatic, this kind of thing, but doesn't solve the problem. Okay. Finally, the final step will be, having done that for a system in which we neglect the off-diagonal elements thanks to the Van Hove argument, which means that the system has to be very short, we will take a large system, slice it into many short devices, short systems in which the argument applies, assuming that each slice is randomized, doesn't have phase coherence between one slice and the next, which is the semi-classical approach, and we'll get the Boltzmann equation. So there are two crucial steps here which justify the statement that I made before of why we cannot derive the Boltzmann equation. One is this little trick. Okay, it's commonly used, mathematically it's ubiquitous, but physically it leaves a bitter taste in your mouth because you think you're close, but you're not quite getting there. You cannot open the final door. And the second one is we have to assume this random phases between the various slices of the system. So we go to semi-classical because there is no coherence between what happens in one slice of our device and the next. Okay, let me go into more details about how we're going to proceed. By the way, this is a picture of Wolfgang Pauli, the first to derive a master operator of the Boltzmann form in quantum mechanics. And this is Leon Charles Van Hove, a Belgian actually, who, as I said, was a director at CERN for many years, and he worked in many fields, from high energy physics to I don't know if you can consider this condensed matter theory. It's a more general. It's one of those papers where we'll go probably into Physical Review A, general physics. So what about this master operator, the master equation that we want to derive in order to justify the form of the collisional integral of the Boltzmann equation? Again, this object. This is what we want to derive. Okay, so that form for a closed system now, the Boltzmann equation is valid for an open system and for a closed system. Pauli derived it in this paper. I haven't looked at it. Boy, 1928, so very shortly after quantum mechanics was invented. I don't even know whether there is a translation in English. Apparently this is actually in a book that commemorates, it's for the birthday of Arnold Sommerfeld. I think Pauli was a student of Sommerfeld, I'm not sure. Anyway, so he derived that form of the collisional operator the way the system approaches equilibrium. If we go back here, forget these terms, we have that the occupation of a state increases and decreases in time according to scattering with the bath. And eventually it will go to equilibrium. You can show that this approaches an equilibrium distribution function. So he derived, ignore this piece, this equals to this, assuming that this system is interacting with the bath. The bath has infinitely many degrees of freedom. You integrate the Liouville-Neumann equation over a short time step. Having solved it for a time step, you assume that all phases which describe the lunar superposition of eigenstate expressed in the representation of the eigenstates of the Hamiltonian, all of these phases cancel out and the off-diagonal terms die. And so you're left only with the diagonal terms of the density matrix. And that's why you have a scalar here and not a matrix, because the off-diagonal elements are zeroed out by the random phase approximation. You have to do it at every time step, which is a very strong assumption. And then you can approach to equilibrium this way. This was 1928. 1955, Van Hoff showed actually that this phase randomization at every time step is not really necessary. He showed that, let me see if I can get the logic right. Take your system as the same system that Pauli assumed. Take an initial state which belongs to either one of these two classes. By the way, he didn't show that this is what I'm going to say is true only for these two classes. Essentially, he said, I found out that for these two classes, what I'm going to say is true. There might be other classes of states, initial states, that are also endowed with the same property, but I couldn't find any. So at least if the system is one of these two classes, the initial state that you assume for your off equilibrium is not an arbitrary state, another combination, arbitrary occupation of all the states, but it's a linear superposition of states of the free Hamiltonian that has a support only over a very narrow range of energies. So you take only a narrow range of energies, you take the eigenstates in that narrow energy, and you form a linear superposition of these states. And this is your initial density matrix. This is your initial state. Alternatively, you can look at the absolute opposite situation. You take an initial state, a combination, a linear superposition of states which spans a broad range of energies, practically all of the energies up to the maximum energy that you have by energy conservation. So in some sense, if you think of electrons being injected into a device, you're talking about either very broad packets. Essentially, a plane wave is a single eigenstate. It's an extremely narrow range of energy. It's a delta function, one energy, okay? So you can broaden it a little bit, and then you have a packet which is extremely broad spatially, but is very narrow in k-space or in energy space. I'm using it as synonymous. They may not be strictly speaking, but essentially it is. In the spirit is the same. Alternatively, you can look instead of electrons which are extremely well localized in space. They're point particles, delta function in phase space. Then they span, in order to build a delta function, you need a uniform distribution of k-states or energies. So if the initial system is in one state which belongs to one of these two classes, at least, again, as I said, he said explicitly, I don't know, there may be more, I didn't find any, but if it is in one of these two classes, then you need essentially a random phase approximation only at the beginning that you're made, but then you're free to go. And then you're led to a master operator to describe the various interaction processes according to equilibrium. Any question about this? This is extremely tricky, I know. And the paper, I actually was given this paper many years ago by Lino Reggiani. I think we were in Tempe, Arizona for a conference, and he gave me this paper, and it was hard to find. Now you can find it online. Actually, I think it's a free PDF. I admit I followed the paper up to a half when he goes on to deal with the onset of irreversibility. I got lost. I have a hard time following it. It's extremely hard reading the whole paper, but that first half I kind of worked my way through. The second half, which is the interesting one, because it shows how these type of interactions, which we will show, which have infinitely many incoherent degrees of freedom, lead you to the master equation, and that sets off irreversibility. If you want, this is my favorite proof, quote unquote, of the H theorem. Not quite there yet. There are some assumptions. There is this tricky Van Hoff limit, but it's as close as it gets. Okay, so let's roll up our sleeves and start. So I have my system. I said it's my closed system for now. It's in thermal contact with a bath. I injected electrons in some off equilibrium condition from the source when the drain is biased high. So the electrons have some energy which on the drain side is very high, so I'm strongly off equilibrium. So I described the system by a total Hamiltonian For now, there are no contacts. So there's the electronic Hamiltonian. And this electronic Hamiltonian will be just a kinetic energy operator, whatever it is. It can be in parabolic bands this form, or using the equivalent Hamiltonian that we have discussed in the past. We can write it this way, using the Cohen-Lattinger expression, whatever we wish, using full band. So the electronic Hamiltonian already contains the potential. So there is a source and drain potential going from high to low, and the electrons are hot, they're accelerated, and I will consider the Hamiltonian and solving this Hamiltonian to find the electronic eigenstates that I will use to represent my density matrix. I will use the eigenstates of this Hamiltonian. So I've already solved the self-consistent Schrödinger-Poisson problem, so to speak, for the closed system. Eventually we'll have to do it for the open system. Then we have the phonon Hamiltonian. Okay, we know what it is. We will not deal with phonon drag, without phonons, with off-equilibrium phonons. I will not even deal with self-heating of the device. So let's ignore these effects. Some of them are easy to account for, some of them are prohibitively difficult. So this is the usual electron phonon Hamiltonian, and we will eventually take them at equilibrium. So this is the phonon Hamiltonian. And this is the electron phonon interaction. We can express any way we wish. So I will denote by little I, j, k, and so on, the eigenstates of the single electron Hamiltonian over here. So the eigenstates of this Hamiltonian, okay, with eigenvalues given by E sub I. This index I can be a general label. It can be a set of labels, kx, ky, kz. If this is 0, these are plane waves. So this index I is a general index, whether it represents a 3-dimensional spectrum, 2-dimensional spectrum, depending on where the electrons are sitting, what is the shape of the potential, discrete, continuum, again, depending on the energy and what is the shape of the potential. Clearly, if I have a well in a potential, I can have discrete and continuum, doubly degenerate, single degenerate, whatever it is. So this is the general spectrum of the single electron Hamiltonian. The phonon Hamiltonian is the usual thing. Now, the electron phonon Hamiltonian, remember I described it in terms of the B and B plus and the C dagger and so on. Here, I write it as the interaction terms in which an electron in state J jumps to a state I. Here, the state I jumps to electron state J by creating a phonon, here by annihilating a phonon, phonon absorption, phonon emission. The matrix element, or the coupling constant that I had here, is exactly what I had before. If you remember, this coupling constant script A for a wave vector of momentum q and polarization eta, except that I'm representing it into the representation of the eigenstates of these guys. If these are plane waves, because this is 0, this f of q will be exactly a of q, no difference. But in general, if these are confined states, they're different states, traveling waves, scatter waves in a given potential, this is the form that I have, easy to do. So I hope it's relatively simple. I take just the spatial dependence of the electron phonon Hamiltonian and take the matrix element over the eigenstates so that I have this matrix element over here, depends on q, the q vector of the phonon, and then the polarization is a little different than what I have because it depends on which two states I'm coupling, because I don't have purely plane waves. Okay, and I suppose that in front of this electron phonon Hamiltonian, there is a dimensionless coupling constant alpha that I will use to expand in power series over. So to use perturbation theory. Okay, this, if you want, is the first approximation that we will have to use. As I said before, the density matrix is a complicated object. I will ignore the phonon part of the density matrix. So I will consider this object, the reduced electron density matrix. I take the density matrix only for the electronic states. So this is a matrix whose diagonal elements, C dagger I, Ci, express the probability that the state I is occupied, or the occupation of the state I, depending on the normalization to the density or to 1, vice versa. Okay, the off-diagonal element Ji is the amplitude that I find a system in a linear superposition of the eigenstate I and the eigenstate J of the free electron Hamiltonian. This is a thermal expectation value. It evolves in time according to the, so not thermal, ensemble expectation value. It evolves in time according to the Liouville-von Neumann equation. And this is the Ket-Bra expression that I need to build a matrix. Clearly, if I take the matrix element ij of this object, having introduced this object, I recover the Ci dagger Cj. Okay, over those states. So I define this object now, and this bracket over here implies also a trace over the phonon state. So I take the trace over the electrons, which is what I usually do here. And the trace over phonons, I take the full density matrix, the full one, I multiply by the electronic component only, and then I multiply by this object over here. So this object tells me, it depends only, if you wish, if you take the matrix element ij of this object, tells me what is the amplitude of the states ij, if I and j are the same, is the occupation probability, if they're different, is the amplitude of having the state in a linear superposition of those two states, but average over all possible phonon configurations, okay? So the phonons are traced out, as we say, okay? So I will consider essentially this object and will write it this way as having already taken the matrix element ij. So I put an ij over here, it will be just this object, okay? This is what we want to evolve in time, find out how it evolves in time. Okay, any question? So this is the elegant way is I trace out over irrelevant degrees of freedom. The truth is I don't know what the heck to do with the phonons. I don't want to deal with hot phonons, off equilibrium phonons, phonon drag, and so on. And I trace them out. I ignore them. Well, I don't ignore them. Here, eventually, I will have to plug in something. This is a density matrix. I have to know what it is. So that's what we have to deal with. And then we'll plug in the, we will assume that the electrons and phonons are decoupled, and I will assume the equilibrium density matrix, Bose-Einstein, for the phonon occupation number. Okay, equation of motion. That's probably the last thing I will do because it will take a little bit of time here. So let's consider now the reduced, and I will not write the EL anymore here. The reduced, maybe I do over here. Yeah, let's consider the full, yes. This is still the full density matrix. The superscript I means that I'm working in the interaction picture, which means that remember that the density matrix evolves in time according to the Schrödinger picture, but not Heisenberg. So here I have for the Liouville-von Neumann equation of motion for this density matrix in interaction picture, I have just the interaction, the electron phonon, because the free Hamiltonian has already been factored out. The electron Hamiltonian is already accounted for by using the eigenstates I and J, and the phonon is because we're assuming they're decoupled, they're equilibrium. So only the electron phonon Hamiltonian comes in. So let's integrate it one step at a time. So let's do an integration. So if I do an integral, I have that at time t, I have the density matrix at time 0 minus the integral of this stuff. And here, of course, I have the same row that I don't know what it is. So let's insert now this into this. So I will replace this row t with the row t that I've gotten from this equation itself, if you want. So in here, I have the row of 0, which is the d. So if I put it in here, I have the I have the row 0 commutator with the electron phonon Hamiltonian, and then I have the integral over this thing, which is a commutator of the electron phonon Hamiltonian with this commutator over here. And I'm integrating over all t prime. Okay. Now, if I do a tracing out that I did here of the relevant degrees of freedom, the time evolution of the reduced electronic density matrix is given by the trace over all the electronic state, the trace over all the phonon states of this object. This is what's called the memory term. It's a memory of what happened at the beginning, where I'm starting from, and then there is this time evolution, okay, in which I'm simply taking the trace of over phonons and electrons over this messy commutator. Okay, good. Right. So the first assumption that I think I mentioned before is I'm assuming that at time equals 0, when I'm injecting this stream of hot electrons from the source before shutting down the door at the source, I will assume that the electrons and the phonons are decoupled. So as I said before, my system is closed, no electrons, I open the door, I inject electrons, I close the door. At t equals 0, the electrons and the phonons have not had time to interact yet. So I can write the total density matrix as a product. Okay, it's a tensor product because they're operators. So this is a funny product in operator space of the phonon Hamiltonian and the electron Hamiltonian separately. And the phonon Hamiltonian I will write as the density matrix in a representation of the Q state. I'm not writing a branch index eta, but in principle I could. So just for simplicity, and I take here as the Fock states. This curly bracket means a set of phonons, each harmonic oscillator Q, excited to some state n sub Q. So it's a sequence of all possible excitations. Eventually, I will take it as the equilibrium distribution function here. Okay, is this correct? This is something that we're going to do consistently in the following. There are some cases where this is not true. There are some studies about, in particular, laser pump probe measurements in which you excite a semiconductor with a high frequency laser, high energy, electroplating electron hole pairs across the gap, and then with an infrared, a low frequency laser, you probe the Raman spectrum of the hot electrons in the conduction band. And the delay between the pump and the probe measurement can be as short as tens of femtoseconds. And so you can monitor by varying this delay and repeating the experiments with the different delay times, you can see the time evolution, how the electrons relax towards equilibrium. So it's a direct probe of what we're dealing with here, how these hot electrons relax. And the problem has been studied experimentally by various people for many years. We started with Dr. Shah at Bell Labs and the famous sub-picosecond spectroscopy, pump probe spectroscopy. Theoretically, it has been studied by many people, and especially the group at Marburg, and they use the density matrix and its time evolution in the Heisenberg formulation. So something similar to what we're doing here, but in a Heisenberg representation. And they've actually bypassed this assumption. And actually, there are, at very short times, at the order of femtosecond timescales, the electrons and the phonons are really coupled. So you have excitations which are very short-lived, in which you cannot tell whether this excited state is really an electron or a phonon. Sort of like hot polaron, which is created at short times. We will ignore this. We'll assume that our times are short, but not as short as having to worry about such a complication. So we will separate the electronic and the ionic Hamiltonian, similar to what we've done to calculate the band structure, but this is not an adiabatic approximation, it's different, okay? The electrons are not responding adiabatically to the excitation that we're creating. They're relaxing in non-adiabatic fashion. Similarly, the electronic reduced density matrix, we will write in this form. So again, it is some matrix elements, if you wish, and these are the Fock states. And these are the diagonal elements. And we will assume that at t equals 0, the electrons are in a diagonal hot representation. We have injected these electrons. They were coming from some equilibrium distribution, a Fermi-Dirac distribution in the source contact. They've been injected. They retain this Fermi-Dirac distribution function, which is fully diagonal. So this is my Fermi-Dirac distribution as a function of the electrons. Okay. Good. Okay. Now we go to Van Hove, and this is the tricky part. Let's focus on the red words that try and simplify this. I told you already quite a bit about what it did, but essentially what it says is, and then we'll see how, if the interactions that we're dealing with, such as the electron-phonon interaction in which we have very many phonons, that all the degrees of freedom, the ionic degrees of freedom of the lattice, very many. Or we have many impurities averaged over different configurations at random without any phase coherence between the various scattering processes and the various configurations. Then you can derive, and as we will see how, the master-like form of the collisional operators, assuming that we have an initial state which is in a given one of the particular state in those two classes that we listed before, at least in one of those two classes, either broad energetically or narrow energetically. And we will think about something which is energetically narrow. So broad, a wave packet which is broad. Why am I interested in this thing? First of all, because, as I said, we want to derive the Boltzmann equation and eventually want to slice the device into short sections. So if I have a packet, the wave packet, this is a tricky issue again. How big is an electron in a device? Let me wave my hands quite a bit and say that the packet is a Gaussian with a half width and half height, which is roughly the coherence length, which is the mean free path for phase breaking processes. Okay. For impurity, it's tricky. I would take the average afterwards. So I would talk about the inelastic coherence length. Okay. So essentially given by electron-phonon interaction. If you look at what is the wave packet broadening so defined in silicon, in a heavily doped source of a silicon MOSFET, 10 to the 21st or high 10 to the 20 dopants and electrons per cubic centimeter, the mean free path that you have because of Pauli blocking and so on, at the Fermi energy, which is about, I forget, 100, 150 million electron volts, depending on the doping, it's long. It's of the order of 50 nanometer. Don't use this number to calculate the mobility because I'm ignoring impurity scattering, which I consider as non-phase breaking for now. Okay, so if I'm dealing with a slice which is only 10 nanometer wide, and my wave packet is 50 nanometer wide, then I can assume essentially that the incoming wave, which is injected, is a plane wave. The electron is everywhere. So it belongs to a class in which the packet is sufficiently broad that it is spread almost uniformly across my entire device, i.e. The injected or the initial state belongs to, forget which class it was, class 1? Where was I? Class A of the Van Hove states, okay? So I can apply the Van Hove argument as long as my region, active region in the device is sufficiently short. Not a big surprise because it's sort of perturbation theory, which means scattering over the entire region is weak, which is of course true if you take a wave function which is localized over a small region. So how do we do that? So let's go back to the Liouville-von Neumann equation for the reduced density matrix that I had before. This is a virtual LaTeX occasionally, the version of LaTeX I was using, and overlaps that thing. Okay, whatever. So we do the tracing out. I have to do explicitly the tracing. The tracing means I'm tracing over the electron things, and this is something that I do by assuming that assuming over the phonons, over all the phonon occupation states. This is a commutator that I have, over here, which is coming from these objects. So I have two pieces, a term in which the electron-phonon interaction matrix element is before or after, because of the commutator that I have to do with the phonon part of the density matrix, and this is what is left of the reduced electron distribution and electron density matrix. Okay, so I can write this term, only this term over here, as the integral. This is the same thing, and then I'm explicitly writing the tracing out over electrons over phonons. The phonons are labeled by Q, the electrons are labeled by whatever is the index that I want to use for the eigenstates of the free electron Hamiltonian. And then I have 4 terms, because here I have 2 terms for the inner commutator multiplied by 2 terms for the outer commutator. Okay, so if I write one of these terms this way, then I can write the 4 terms, 1, 2, 3, 4, that come out from the commutator by using this expression. I have 4 terms. This is already a good sign. It's a hint that we're going to get somewhere towards the master operator. It's premature to have hopes at this stage, but the master operator essentially has an in and out terms, 2 terms, but each of these terms is given by a phonon absorption and phonon emission, an in scattering term and an out scattering term. And so we're going to have explicitly 4 terms, and that's what we're looking for. So hopefully these 4 terms will lead us to the 4 terms that we want from the master operator. So again, I have to write these 4 terms. I write them that way, and now I will have to use the fact that I'm tracing out over the phonon degrees of freedom by summing over all the phonon states. So, and this is the phonon density matrix at 0, which we will assume to be a thermal equilibrium. Okay. So the idea is that here we're going to have, because of the electron phonon Hamiltonian has the B and B daggers, we're going to assume that every time I find a term of the order B dagger B, remember, this is the phonon number, so to speak. I can write it in terms of the phonon occupation numbers and only diagonal. So the off-diagonal elements vanish because I'm assuming that the phonons remain at Bose-Einstein thermal equilibrium. Okay, and the B dagger B is just a phonon number. The B dagger is, I can commute the 2 because they satisfy the commutation rules. I still get the delta function is diagonal, and I get the 1 plus Q. And this is where I'm going to get the Einstein's coefficient from phonon emission and phonon absorptions. Okay, and we will take them to be at thermal equilibrium. So having done that, now what we have to do is to write explicitly the time evolution of these objects. Remember, these are the operators that evolve according to the Heisenberg representations. So the states, these states over here, not the CC dagger. They're the states that have to evolve in time. These states over here. Okay. So I take the electronic component and the ionic components, what I get from those states that I had, and I can write them in terms of the states at t equals 0. Now these are the t equals 0 states. I have taken out all the matrix density matrices outside over here, and then I've taken out also the coefficients of the electron phonon Hamiltonians that I had before, which require states which are over the various states m's that are over here, and the intermediate states that I get from the electron phonon Hamiltonian. So I can write it this way. Notice that I've added the sum of intermediate states that I have. Okay, so this is the explicit form of the integral that essentially I have to deal with, which is this term. Okay, I remind you, when I've written down explicitly these forms, where is it? Somewhere, I wrote it somewhere. Here, for the electron phonon Hamiltonian, okay? So there is a sum over I and j that I have to repeat, and that's where these indices R, S, and so on come in. Where am I? Right here? I lost it. Here, okay. All these indices, L and M, H and R, the L and M come from one Hamiltonian, electron phonon Hamiltonian, H and R from another electron phonon Hamiltonian. So unfortunately, the painful part of all of this derivation is the number of indices that I have to take around. So beyond the algebra, let me give you an idea what will happen now. This is an integral. It's very similar, and we will actually find out using the Van Hoff argument how to simplify this integral. This integral will have a singularity. Will lead us to a singularity when I want to sum over the energies. Because if I do the integral over time, I will get the denominator, which is essentially the sum of this term and this term. And for some particular Q, some particular L and M and H and R, I have poles, singularities. How do I integrate now over, remember these are integration over L and M or over Q. I'm using sum, but we go to a continuum limiter integration. How do I integrate 1 over x minus x naught? I hope you remember that. I integrate it by changing, by expressing that into an integral over the, which is only the Cauchy principal part of the integral over that singularity. And then there is a minus plus I pi times the delta function of the argument. How do I get that? I get by regularizing the integral. If you remember, we had to go around the pole, either moving the pole up or down, so integrating over the little small loop in an upper half circle and a lower half circle. I hope that you remember that. That's a regularization. Formally, it comes by adding, multiplying this term by an exponential, real exponential in time. These are complex exponential. I want a real exponential. With a plus or a minus here, depending on what I wish. Either it's a retarded or an advanced formulation, whether I move the pole up or down. But no matter what, I have to multiply this in order to regularize the integral by a real exponential. And this, depending on the choice you make, is what sets the reversibility. This is what now, this, if you go from t to minus t, doesn't change. Once instead I've made a choice for the sign, if I go from t to minus t, I get the opposite of what I started from. So it is this regularization of this integration that we'll have to do, simplified. This is still very messy. It involves all virtual states, all virtual states which are off diagonal. You see how many indices L and M and I and J that I have here. It's a 4-particle density matrix right here. So strongly off diagonal. How to simplify it to a diagonal form. And this is the last step that I want to make. Go to the Van Hoff argument. We started with somewhere here, we have terms, 4 terms, and each of them have 2 electron phonon Hamiltonian, because we are at the second order in alpha, right? If you had to extract an alpha out, we would have an alpha square over here. This term, we'll see that we can let it vanish. Although memory effects are quite important in some situations, but in our case, we'll ignore it. Assuming that this is purely diagonal, they're both diagonal, they will vanish. But this is the term we were interested in, and we will stop at the second order in Hamiltonian. So we have these terms, which have 2 electron phonon Hamiltonians calculated at 2 different times. One is coming from the first integration that we did, and one is coming from the second integration. Good. What we do is to what the standard terminology, jargon, is we insert a completeness. You remember that the sum over these states, over all the Fock states over here, these are all possible states in Fock space. So this is a complete basis in Hilbert space, Fock space, provided it's a Hilbert space. Let's call it Hilbert. Then I remind you that this is equal to 1, is the identity matrix. Okay, I hope you remember that this is a funny way to express 1, the identity matrix. So I split the 2, I insert an identity matrix here, and then I expand and express the identity matrix as a sum over these intermediate states. Now look what happens. I'm summing over intermediate states, and these are intermediate phonon states, because I'm summing over all the phonons. Okay, so the number of phonons that I have is huge. So look at what happens about this is a matrix element between a particular state and an intermediate state. All of them. This is an identical guy. So it expresses the transition from this state, which is Hamiltonian applied to this object to the final state, which is this guy, unless the phases of these two terms, when summing over all the intermediate states, are, well, the same, but this is the complex conjugate, so the same or opposite, so they cancel out. Then I have so many different phases, depending on what this guy is, that can contribute to the sum. These are also many electrons, okay? So I have so many phases that can interfere at random when I and j are different, that the number of terms that I have is essentially of the order of the number of electronic states that I have. So I have something which depends on linearly on the number of degrees of freedom. If instead I and j are the same, then you see that I can bring out over here this guy on this side. It commutes with the Bose operator that I have here. I bring it over here, and then I have exactly the same initial and final states if I is equal to j. I is equal to j. So if I is equal to j, the phase of the final state is the same. I'm summing over the same intermediate states, so the two phases are equal and opposite. And so they cancel. And so I get 1. So when I have off-diagonal elements of the reduced electronic density matrix, then the number of states that contribute to the sum is linear, grows linear with the number of degrees of freedom that I have. Random cancellation of the phases. Because I contribute to only those states for which the phase is cancelled, which is order of n. Instead, if I consider the states, the particular case in which I is equal to j, so the diagonal elements of the density matrix, the phase is cancelled for all of the intermediate states. So I get something of the order of the square of the number of states. And this is the main Fanov argument. It's based on the fact that I'm dealing with a large number of degrees of freedom of the bath with which I'm interacting and the large number of electrons that I have. So for example, I don't know if I'll go into enough detail to see it. If I'm dealing with an electron-electron interaction, I can follow an argument similar to this one and reach the same conclusion that the electron-electron, the short-range electron-electron interaction is of the Van Hoff type, so that only diagonal terms survive of the density matrix, only if I have many electrons. If I have a quantum dot with 3 electrons, that's not true. Then I cannot describe the scattering operator that I have in terms of a master operator. So the Boltzmann equation cannot be derived. If I have 10 to the 23rd electrons, then yes, then I can definitely do it. Of course, there will be a fuzzy gray area in which I have a dozen or 20 electrons. And it's not clear whether the phase randomization is valid or not. But in general, the loss of coherence, because that's what we're talking about, is extremely fast. So only with a few electrons, you already get total decoherence. The analogy that I have is a classical analogy, actually, but the billiard balls. If you play 8 balls, and rather than 8 balls, you play 3 balls. And you put a triangle of 3 billiard balls, and you break the triangle, and you play a movie. And this happens if you have only 1 billiard ball, and you play the movie forward or backward, you cannot tell the difference, ignoring the friction of the pool table. If you have 2 balls, you may have a hard time distinguishing which is the forward and backward motion, except at the initial state. It sounds funny, but in the subsequent time evolution, it's hard to tell. If you have 3 or 5 or 7 balls, then it's immediately obvious, already with such a small number, that the system is becoming irreversible. And the same happens for the loss of coherence in quantum mechanics, which is actually one of the problems in quantum computing. It doesn't take much to kill the coherence. So the basic idea, remember, is inserting a completeness over all intermediate states. If you want, we can move this on that side, looking at the situation in which the phases are equal and opposite between these two. This can only happen when this is, view it without bringing the C dagger over here. This is a number operator acting on some state over here, and you get the same phase acting on an eigenstate. Okay, if I and j instead are different, you get a different phase because you get a different state, and so the phases of these two is not going to cancel. And then you get all the random phases that you can add. You can adapt by summing over these intermediate states. So this is the crucial argument that Van Hove made. For example, dealing with impurities, this is not true because the phase is the same. It's not phase breaking. So the phase, no matter what state you have, you still have the same phase. So given this Hamiltonian over here, which doesn't break any phase. So in that case, actually, you can see that it's the configuration average of the impurities which will create this situation, a situation which is similar. Okay, and we will discuss it in the future, next week. So from now on, let's remind you the random phases of these off-diagonal elements that you have coming out of the very large number, infinitely many degrees of freedom that kills the off-diagonal elements. Having done that, we will have to make more approximations, but still we will not reach the master equation until we finally go to the final step, which is taking the Van Hove limit. Okay, I'll conclude here for the day. Oops. It's running too fast forward. Let me. Okay. So if there are no questions, everybody happy? I apologize, it's messy, but I think it's useful to understand one of the possible ways to derive, quote unquote, the Boltzmann equation, the multitude of approximations, some of them questionable, that we have to make. Okay. If not, thank you, and I'll see you next week. No questions?
Ciao Massimo.
I have to talk to you about exams.
Anytime.
How to set them. A new process for me.
Okay.
Okay.
No problem.
Bye-bye. Have a good weekend.
Bye, Massimo.
Everybody.
Bye. Bye. Ciao.
Bye-bye.
Ciao.
Ciao, ciao.